You've heard me talk a little bit about John Dalton already, and I'm just going to talk briefly about him again. I wanted to remind you that he was doing his research over 200 years ago in the early 1800s, and one of the amazing things that he figured out was that elements always react together with the same mass ratio. What I mean by that is if you had sulfur and you weighed out 32 grams of sulfur and then you reacted it with oxygen and you found that it reacted with 32 grams of oxygen, then these would be a 1-to-1 mass ratio. So if you had 6 grams of sulfur, it would react with 6 grams of oxygen. If you had 900 grams of sulfur, it would react with 900 grams of oxygen. It would always keep this same mass ratio. He also found that some elements react in more than one mass ratio. So, for example, let's say if you use 6 grams of carbon and it reacted with 8 grams of oxygen, then this would make compound number 1. And you could make compound number 1 again if you used 12 grams of carbon and 16 grams of oxygen. In other words, you doubled the amount of both of these. Or if you did some kind of wacky multiple where you did, I don't know, maybe like 24 grams of carbon. I'm trying to make my math easy for myself. And 32 grams of oxygen, so I just multiplied this by 4. And here I had multiplied it by 2. All of these, if you reacted them together, would make compound 1, whatever it was, since he didn't know what it was. But you could also take 6 grams of carbon and 16 grams of oxygen and react them to make compound number 2, something different. So in this case, we have a mass ratio that's like 1 to 1.5 or something like that. Is that right? Let's see. No, not quite 1 to 1.5. This is 6 and this is 8, so that would be 3 to 4 mass ratio for this compound number 1. And you don't need to remember the mass ratios. I'm just trying to illustrate this. So with this other ratio where we use extra oxygen, we make a different compound that's different from this compound 1. And we know that these are different because they have different chemical properties. But if you double your masses here, and you double both of them, so instead of 6 grams of carbon, you use 12 grams, and instead of 16 grams of oxygen, you use 32 grams of oxygen, then you still make compound number 2. So here we have 2 separate mass ratios that reliably will make the same compound. And so this whole thing together, this principle of these mass ratios staying consistent, is called the law of multiple proportions. And Dalton used this to figure out what elements reacted together, and he used it to determine what we call empirical formulas. Which is the simplest ratio of the elements for each other. And don't worry too much about empirical formulas right now. they'll make a lot more sense in a little while after we start talking more about different kinds of compounds. So I just wanted to throw this vocabulary term out here because we have some evidence that we need to hear terms multiple times in order to remember them. I think when I was reading up on education, we need to hear something at least 6 times before we can learn it. And so this is why I do a lot of repetition. Okay. So when we categorize the compounds, I'm going to kind of switch topics a little bit, mostly sidestepping topic here. When we make compounds from multiple elements, we categorize them mainly as 2 main categories: ionic compounds and molecular compounds. These are sometimes also called covalent. So you may have heard either term before if you've studied chemistry before. Okay, so these are our 2 major classifications. These are not the only classifications, but they're the 2 main ones we're going to talk about in general chemistry. So don't worry if you hear about other ones. There are more, but these are the 2 main ones. All right, so how do we know if something makes an ionic compound or a molecular compound? So if we have an ionic compound, we are going to have typically a metal and a non-metal component. And over here for molecular compounds, these are going to be all non-metals. And I'm talking about which elements we're using. And this is why it's important for you to be able to figure out if something's a metal or a non-metal. And I'm going to put a little asterisk over here and say, with a few, there's always exceptions, with a few semi-metals thrown in. But we'll mainly stick with the non-metals. And then I'm going to have and 1 or 2 non-metal, or excuse me, non-metal cations. But these are the easiest classifications for how to look at whether something is an ionic compound or a molecular compound. And so if you're just getting started on telling the difference between these 2, this is how I would approach both of these categories. Is I would just look at, for ionic, metal plus a non-metal, and for a molecular compound, all non-metal. And when you're a little bit more experienced with chemistry, you can start messing around with some of the, specific exceptions and stuff. But we don't need to worry too much about those exceptions right now. We're just going to stick with these 2 big categories. So let's talk about what these compounds form. Okay? These guys, they make compounds because we have bonds that hold the atoms together. And these are chemical bonds. And each bond is individually between 2 atoms in a compound. So when we have non-metal elements, these atoms will share some of their electrons. I'm going to draw a picture here. Remember how we looked at the structure of the atom and we said, all right, we've got this little nucleus here that's small and positively charged where the protons and the neutrons are, that are all packed in. And then we've got some electrons hanging out around the outside. So if we think about what's happening between our atoms, and we'll look more at atomic structure in a little while, but if we think about this, we're going to have some attractive forces happening between our electrons, and because they're negatively charged, and the positive charge from that nucleus. And then that's true both directions, right? So when you make a covalent bond, the atoms sort of rearrange themselves so that they share electrons, and we call this a covalent bond. And it's specifically two atoms share electrons in a covalent bond. And we'll talk more about the details of that a little bit later on. So for now, we can just remember that a covalent bond has shared electrons, and it's between two atoms. For an ionic bond, we have two atoms that are involved again, but one gives up one or more electrons, so it becomes positively charged, and this is called a cation. And the other accepts the electron, or one or more electron, to become negatively charged. And this is known as an anion. The metal is always going to become the cation, and the nonmetal in the ionic compound will be the anion. As I mentioned, there's a couple of exceptions where we get a nonmetal cation, but it's unusual, and I'll show you more about that later. Okay, so let's look again at our atoms, and we'll think about how this is going to look. Okay, so let's think about a sodium atom. So remember that with sodium, let's do a quick review of isotope notation and look at how many protons, neutrons, and electrons it has. So let's pause the video for a second, go grab your periodic table, and then come back with this information in hand. All right, hopefully you took a chance to do that. So I hope that you discovered that the most common isotope of sodium is sodium-23, and its element number 11, which means that we have 11 protons and 11 electrons, and then we have 23 minus 11 is equal to 12 neutrons. So just to review again, remember that this atom has its protons and its neutrons jammed into this tight little packed massive area called the nucleus, and it's the electrons that are out here. So when the sodium becomes a cation, because remember, sodium is a metal, and it's going to lose one electron and become sodium plus. It does that because it loses one electron. So sodium plus still has 11 protons and 12 neutrons. It's still sodium-23, 11. It just has one fewer electron. It only has 10 electrons now. So I'm going to say this again. It might sound repetitive, but I want you to be really, really sure. When you make cations and anions, it is the electrons that are changing. Remember, those electrons are the ones that are outside the atom. They are the ones that we can actually move around. The protons and the neutrons are jammed in that nucleus, and just forget about it. You can't do anything to the protons and the neutrons until we start talking about nuclear chemistry, which we won't for a while. Okay? So I want you to really focus on thinking about what that proton and what that neutron, that they are unavailable and only the electrons are involved in making bonds, and only the electrons are involved in making ions. Okay? Now, one of the great things about the periodic table is that the periodic table actually tells you a lot about which kinds of ions are formed. So ion information is available in the periodic table. Now you can't just automatically figure out every single one, but there are a lot of hints, so it's very helpful to get familiar with it. Let's take a quick look at this figure from the book. Do you recognize where we are in the periodic table? Check it out. Here we are in column 1. All of these elements form +1 cations. Look at column 2. Here we have +2 cations. Column 3, +3 cations. I'm going to skip over here for a little while. Now we're over here. These are the noble gases in column 18. And check it out. All of the halogens, they form -1. All of the column 16, they form -2, at least down to tellurium. And then over here, the nonmetals in group 15, they form -3. So I think about this looking at where I am. Here's the edge of the periodic table, and I say, okay, I'm 1 over from the edge on the left-hand side, this is going to be +1. I'm 2 over from the edge, that's going to be +2. I'm 3 over from the edge, that's +3. Yes, the rest of these transition metals and some of these post-transition metals, they have multiple ions, and it can get a little confusing. But look, 1, 2, 3. So we do have some nice trends here. And the same thing is true over here. I say, all right, here's my noble gases. My halogens are 1 over from that, so those are -1. This group 16, these are 2 over from the halogens, so that's -2. These are 3 over from the halogens, so that's -3. So the periodic table can tell us a lot of useful information about what kinds of ions form. So I use this as a tip, as a key, and then the rest of these ions, so all of these ones in figure 2.2, I will hold you responsible for, but not this week. We'll have lots more practice before I start to expect you to remember what ion charges are, and there's also going to be a lot of clues that help you figure out what the ion charges are. So it's a lot easier than you think. But now is a good time to start doing some flashcards.